We're going to come back to this chart, which we talked a little bit about in lab. This is the classical coagulation cascade. Now remember, in order to really form a true blood clot, one that's going to stick and keep you safe from bleeding out, you have to form this stuff, an insoluble fibrin polymer, also known as a clot or a thrombus. Thrombus we don't want, but they get formed in the body anyway. And there's two ways to activate this whole system in order to get this end result. You can go the intrinsic route, which is just a clot formation in the vessels. There's no external tissue damage that's triggering it. Or we can go the extrinsic route, and remember that's going to be when you actually damage your tissue. You're going to have something called tissue thromboplastin that gets introduced into the blood, and that's going to stimulate a clot. Here, the clot stimulus will be some of the chemicals that the platelet has, whereas here, the clot stimulus are going to be tissue chemicals. So this is your intrinsic pathway up here. This is your extrinsic pathway, and they both meet down here in the common pathway. So regardless of how they get to this point, both the intrinsic system and the extrinsic system share this fancy common pathway. And remember, each of these is a protein, and each of these arrows shows the conversion of a protein from essentially an inactive form to an active form. It's pretty complicated, as you can see, and we're not going to get into specifics, but it definitely shows you that everything has to be working perfectly in order for this thing to happen. If you have an issue with factor 7 and it doesn't get converted to factor 7A, you're not going to form a clot this route. If you have an issue with factor 10 and it doesn't get converted to factor 10A, you're going to have an issue clotting in this route. And this is really dangerous because this is the intersection of intrinsic and extrinsic. So even if this is working fine and that's working fine, if this doesn't work fine, then we're going to have big problems. So the first test we have that will measure these intrinsic and extrinsic systems is the prothrombin time, which we did perform in lab. And if you remember, it will measure the extrinsic pathway, the functioning of the extrinsic pathway, and the common pathways. What it does is it literally measures the time it takes for a clot to form. You probably remember this lovely looking fibrometer here. And if you remember, what we did is we had some anticoagulated blood using citrate, which bound up all of the calcium and basically precipitated it out so that it was not able to be used. You added to that plasma, you added thromboplastin, which is the tissue factor that comes out of the tissues upon damage, and calcium in here. And then the fibrometer dropped and it mixed, and the time it took for a clot to form was recorded. There is a little bit of a updated machine down here. This is KC1 Delta, and I believe we have this in the lab, and you will be seeing it maybe in the future here. So it's an important thing to think about. But there's an easier way to do it. This one physically measures the formation of fibrin. Here you're going to use more of a turbidometric measurement. So as it becomes more turbid, that's going to indicate that there's a clot formed along those lines. So remember, the PT or pro time or prothrombin time measures the extrinsic pathway and part of that common pathway or the common pathway. The activated partial thromboplastin time, or APTT, or just PTT, measures the intrinsic and the common pathway. And I found this little helpful device to remember which test measures which pathway. And if you look here, the PTT, the two T's here are in a relationship, so it measures the intrinsic pathway. And in the PT, there's only one, so they are X's, and that measures the extrinsic pathway. I wish I could take credit for this. I didn't make it up. This firstaidteam.com did. So hopefully that helps keep straight which test measures which pathway. But just like the PT or the ProTime, the APTT measures how long it takes a clot to form. The major difference is that this is a two-part or two-step test. You'll have your citrated blood, actually it would be plasma, not just blood, And what you add to it is a fake platelet substitute, essentially. Since platelets are what are going to be one of the things that activate the intrinsic pathway, you have to add platelets or something like platelets in to cause this coagulation cascade to occur. So you add the substitute, you add another activator which helps in the conversion, and you add calcium. And you do this in 2 steps. First, you're going to add in, I believe, the platelet substitute plus the activator, and then you're going to add in the calcium, something along those lines. But it gets split into 2 physical pushes of the button because you have to add 2 different things at a time. Again, you're going to record clot formation. How long did it take for that intrinsic pathway to run its course and form a clot? And you can kind of help to diagnose intrinsic issues or common pathway issues with this. Now, the fibrinogen assay is a modified thrombin time test. There used to be a test called thrombin time, which looked just at the common pathway and its functioning. However, they don't really do it all that often, and so they've switched to this test called the fibrinogen, which kind of measures the same thing. It's going to give you a clue as to how your common pathway is functioning, and it's going to allow you to measure your fibrinogen levels and if the fibrinogen is functioning correctly. So what a fibrinogen test or fibrinogen assay is going to measure is the amount and function of fibrinogen, and it's also going to look at the common pathway. Also, it measures the time it takes for a clot to form. And in order for this to happen, what you're looking at are, you're going to take your diluted plasma, so you're going to dilute it out a little bit, and you're going to add thrombin to it. And if you remember, thrombin is an important part in that very end step in that common pathway. And if you don't remember, go check it out. It's going to convert fibrinogen to fibrin, and that's a really important step. You're going from insoluble to soluble there. So you add thrombin to the plasma and you measure the clotting time. Now, the less fibrinogen you had, or the worse off the functioning of the fibrinogen, the longer it's going to take to clot. So a longer time in a fibrinogen assay correlates to less fibrinogen. And there could be a couple reasons why this might be happening. For example, you could have something called DIC, disseminated intravascular coagulation, and all your fibrinogen is getting used up in all these tiny little clots that circulate throughout your body or get stuck in places throughout your body. And if that's the case, your fibrinogen levels will be low and your fibrinogen assay time will be high. And so what will happen is when you get that clotting time down with this test, you can use a standard curve that you would have set up and say, okay, it took this long, and that means I have, this should be like time. It took this long, which means I have this much fibrinogen in my sample, which might be a little higher than normal, it might be a little bit lower than normal. You could look and see. But the longer the time it takes to clot, the less fibrinogen you have. And here the reason why this says OD 450 is because, again, this is turbidometric. So when the clot forms, the time it takes to get to a certain density can be measured, and then that can be correlated to how much fibrinogen there really is. So this has replaced this older thrombin time test that used to be done. It's not really done anymore. It's just a fibrinogen assay. The last test we're going to talk about is the D-dimer test. And what's different about the D-dimer test is it doesn't actually look at how well your clotting process is happening. It's looking at your fibrinolysis process. So the breakdown of those clots that you made, are you clearing them appropriately, or are you finding the remnants of a clot in your blood, indicating that somewhere in your body there might be a potentially deadly blood clot? So the D-dimer test tests for fibrinolysis, and because the enzyme that promotes fibrinolysis is plasmin, it's also a reflection on your plasmin activity. What it will do is it's going to look for something known as D-dimer molecules. And I have a little flow chart here. Basically, this is your clot with the fibrin in it, and this is the plasmin. And what will happen is once you've had your clot for long enough and we're ready to get rid of it, plasmin will convert it to this monomer known as X, factor X, or just X. And then through a series of steps, X will be broken down into two parts, Y and D. And then Y will be broken down into two parts, D and E. So every time you have fibrin being degraded, you're going to have two D molecules created. So that's the D dimer, those two D molecules that are created. If you have excessive clot breakdown, your D dimer levels are going to be higher. So you can measure this. You should have a little bit of this in your system at any point, but if you have a clot or you're clotting and you need to, and it's being broken down rapidly, you're going to find an increase in D dimers. So how do we measure this? Well, you get your citrated plasma and you mix it with latex beads that are coated with anti-D dimer antibodies. So we have antibodies for these D dimers here. What that will do is that will cause agglutination, and again, through those, through a spec or through a turbidimeter, we can measure how much agglutination has happened and measure the concentration of D dimer antibodies. So it's an interesting little test. The goal of our discussion today was to look at some common hemostasis, and coagulation tests performed in the lab. If you have any questions, you know where to find me.